Good day. Today's session is on heat exchangers. Heat exchangers are used to move thermal energy from one place to another, and they are usually configured as part of a thermodynamic cycle in power systems or used in heating or cooling and air conditioning systems. So let's go ahead and look at a shell and tube heat exchanger, which is typically used as a condenser or boiler in power systems. With the shell and tube heat exchanger, there's a shell that then has many small tubes in it that are connected by headers, and cold water or some cold fluid will come in and be heated by, typically if it's a condenser, by steam in the shell side, which will then condense to water. And the steam will come in, and there'll be baffles to essentially swirl it around the tubes, and then it will leave having changed phase. And when one looks at a heat exchanger, one typically first draws a temperature distance diagram with the temperature profiles of both the hot and the cold side. Since we have a condenser, we have steam coming in on the left, and as it changes phase to water, it transfers its latent heat to cold water coming in, or cold fluid, and that will then rise up in temperature. So we'll have hot outlet, cold inlet, hot inlet, and cold outlet. That's typically the configuration of a counterflow heat exchanger. Now, when we're dealing with HVAC systems, what's typically done is a heat exchanger that accommodates an air side and a water side. And if we just look at a heating coil that you'd see in an HVAC duct, there will be cold air coming in from the left, and it will encounter thin tubes that will contain hot water circulating back and forth, and then that heat in the hot water will be then transferred to the cold air, and it will come out at a higher temperature. Typically there are multiple rows, and they're connected in various arrangements, series and parallel. Lots of vendors, lots of people make these, and you can see their catalogs online. Now, if we have enough rows in this crossflow heat exchanger, we typically model it as a counterflow, and that would then be what we had in the previous page with the fluids coming in opposite directions. And taking a closer look at this heat exchanger, we'll just see tubes with many fins on them. So how do we model that? Well, first off, we go ahead and use an overall heat transfer coefficient, U, that includes the air side, the tube wall, and the water side heat transfer coefficients. It also includes the fin efficiency. I haven't included that in this particular equation. And that in many cases that's given to you in a problem, or you would just calculate that yourself before you tackle the main problem. Now in a counterflow heat exchanger, I'll just draw this again, for just sensible heating, we'll have one fluid coming in again from the left, cooling down, another fluid coming in from the right, heating up, and there'll be transfer of heat from the hot to the cold fluid. And here's a little very simple schematic of the counterflow of the two fluids going in different directions. Now, previously in class, we've accounted for that changing temperature difference between the hot side and cold side by defining a log mean temperature difference, which is really just the temperature difference on one side minus that on the other side divided by the logarithm of the ratio. When we have that log mean temperature difference, then we can form a Newton equation that looks just like our typical HA delta T equation. Now, if we know all the temperatures coming in and out, this is just a great way to find out what the heat transfer is. But in many cases, we don't really know what the outlet temperatures are. So Professor Bill Kays at Stanford in 1942 developed an effectiveness-Ntu method, and it uses the same energy equation, a Newton equation, but just configured a bit differently. So what is effectiveness-Ntu? The effectiveness is the actual heat transfer divided by the maximum heat transfer. What's the maximum? Well, if you go ahead and just kind of think about it logically, it turns out that the maximum heat transfer is one where the side with the smaller flow rate times specific heat will have the largest temperature change. And when you multiply the flow rate times specific heat times the maximum temperature change, that's the maximum heat transfer that you can have. The book has a nice explanation of this as well. So that then means that the actual heat transfer will be the effectiveness times the m.Cp, the smallest value of the two, times the maximum temperature difference. And what Case did in his classic paper is show that the effectiveness is a function of two variables. One called Ntu, the number of transfer units, and the other one the heat capacity ratio. Number of transfer units is the heat transfer coefficient times the area divided by the smallest value of m dot times c. And the heat capacity ratio is just the ratio of the minimum to the maximum value of the flow rate times specific heat. And that typically will be numbers between 0 and 1. And the NTUs will be typically between 1 and 5. And when you look at it graphically, when you plot effectiveness versus NTU with the parameter of the heat capacity ratio, the curves look like rising exponentials. And then finally, what do those curves look like mathematically? Well, this is where Kayes showed how simple things can be. We're primarily just going to look at counterflow analysis. The effectiveness is just equal to this function of NTU and C star. And if C star is equal to 1, which means the flows are balanced, we have an even simpler equation, NTU over 1 plus NTU. In some cases, we need to know the area, so we just go ahead and solve for NTU as a function of effectiveness, and we get this logarithmic form right here. If we have to deal with a cooling coil in an HVAC system, we need to think about the condensation on the cold fins, but that's outside the topic for this class. Okay, thank you very much.